Answer these questions yourself before you continue. What is Q and what kind of electrochemical cell is this? This is a galvanic, also called Voltaic cell. We can see that by the fact that there is no battery in the cell. Instead, this is the battery. A spontaneous chemical reaction sets up a potential difference. So chemical energy is converted into electrical energy. If the two half reactions of a galvanic cell happen in separate containers, you have to have a salt bridge, also called an ion bridge, between the two containers to complete the electric circuit through the movement of ions in the bridge. We're told that the mass of the aluminium electrode increases. Let's make sense of that. We find aluminium in this table of standard reduction potentials. Since this is a reversible reaction, either of these reactions is possible. Soluble aluminium ions, Al3+, could be gaining electrons to become solid aluminium, Al atoms, or solid aluminium atoms, Al, could be losing electrons to become soluble aluminium ions, Al3+. We're told that the mass of the aluminium electrode increases, so we know that it must be this half reaction that's happening here, because only this reaction would increase the mass of the electrode as aluminium is deposited on the electrode. Solid aluminium is deposited on the electrode. Remember that oxidation is the loss of electrons, accompanied by a rise in oxidation number, and it always happens at the anode. Reduction, oppositely, is the gain of electrons, accompanied by a drop of oxidation number, and it always happens at the cathode. In a voltaic cell, the anode is negatively charged and the cathode is positively charged. Remember, that's the opposite of what it is in an electrolytic cell. The reaction that's happening at the aluminium electrode must be reduction because electrons are gained. Notice how aluminium's oxidation number drops from +3 in the Al3+ ions to 0 in the neutral Al atoms. Reduction happens at the cathode, which is positively charged in a voltaic cell. So we know that the aluminium electrode is the cathode and it's positively charged. Just notice the reason why it's positively charged. The spontaneous reaction happens first, and the charge on the electrode is a consequence of this. So the aluminium ions gain electrons from the electrode, and that fact makes the electrode electron poor because electrons are being sucked out of the electrode. So that makes the electrode electron poor. And another way to say electron poor is positively charged. So we know that the aluminium electrode is positively charged, and it's the cathode where reduction happens. And so from all of this, of course, we also know some stuff about electrode Y. It must be the negative anode at which oxidation happens. Electrode Y is surrounded by Y2+ ions. So here are two possible reactions to occur at electrode Y. Either the Y2+ ions can gain electrons to precipitate as solid Y atoms, or Y atoms in the electrode can go into solution as they lose electrons to become Y2+ ions. Which one actually happens? Well, we know that oxidation must happen here. So which of these is oxidation? This must be the oxidation half reaction which happens here, because this reaction shows a loss of electrons. And also notice how Y's oxidation number increases from 0 for the neutral Y, the solid Y, to +2 for the Y2+ aqueous ion. So here we have a summary of what's happening in the cell. Now we're asked what happens to the concentration of aluminium ions and to the concentration of Y2+ ions. So we go back to our summary. At the cathode, aluminium ions are being reduced to aluminium. So the concentration of aluminium ions decreases. At the anode, Y atoms are being oxidized to Y2+ ions. So the concentration of Y2 plus ions increases over time. We've already answered what the half reaction is that takes place at electrode Y. Now we're asked to give the cell notation. Here's an example from a different cell to remind us of how to write cell notation. We have the two electrodes on the outside, the anode on the left and the cathode on the right. Then we have the ions which are in contact with each electrode next to each electrode, separated by a stripe. We must also give the concentration of these ions. These solutions are joined by a salt bridge. We give a double stripe to indicate the presence of the salt bridge. Now apply that to this cell. We have the electrodes on the edges, anode on the left, cathode on the right. We've already seen that the aluminium electrode is the cathode and electrode Y is the anode. We write the ions, each one is bathed by, separated by a stripe. We haven't been told the concentrations of these ions in this particular question, so we can't add that information. We put in the phases. The electrodes are in the solid phase and the ions are in solution. Then don't forget the double stripe in the middle to indicate the salt bridge. Now we're told that the potential difference that develops between the two electrodes is 0.7 volts as long as the cell is in standard conditions. From that information, we must find out which metal Y is. We know that standard cell potential equals the standard potential of the cathode minus the standard potential of the anode. We're given the standard potential of the cell as a whole, 0.7 volts. As we've already discussed, the aluminium electrode is the cathode. We look at the table of standard reduction potentials and we find that this half reaction has a standard potential of minus 1.66 volts. So we substitute minus 1.66 volts into E cathode. Now we need to solve for the standard potential of the anode. Make sure that your algebra is correct. You must especially be careful of working correctly with the signs. We find the answer to be minus 2.36 volts. How can we see which metal Y is from that information? We go back to our table of standard reduction potentials and we look for this value, minus 2.36 volts, and we find that it's associated with magnesium. So that tells us that electrode Y is magnesium. So this then is the summary as well as the cell notation for this cell that we've been discussing in this question.